For today's quiz, we want to talk about sound. We take it for granted, most of us. This is a tuning fork, and it's an E320, and I can hit this, and you can hear that beautiful tone. How do we actually hear? And is it possible to see sound? In other words, can we represent sound visually? That's what our quiz is all about today. I'll hold that up now. You'll notice that I even put a few icons on here to help students get started. We have an ear, we have musical notes, we have earbuds that we put in there. Whatever their ideas are, have them mark them down, enlist their confidence about what they're putting as their representation. Student responses will vary greatly on this quiz. And remember, these quizzes are to engage students in dialogue. They're going to probably end up wanting to show each other what they put. There's going to be a massive range here. You're going to have a movie with a romantic scene. You're going to have, waves at the ocean, maybe a wave crashing or something, that sound, or a train whistle or something like that. But remember, at the very end, we did ask them to try to represent this physically. And they're going to ask for clarification. And they'll say, what do you mean, like, physically? And we can say, well, physically, how do we hear? Physically, how do things make sound? And they might say, you mean all the way down to atoms? Yeah, try to get it all the way down to atoms. So those are the typical responses we'll get. As we try to provide an explanation for sound and this phenomena, you might want to give your student enough hints to keep them going, depending on what grade level you're working with. But let's just remember that when we strike this, I caused a vibration, and that's really what's happening here. Can't see this very well. Maybe I can get a close-up. But you can feel it. If you have enough of these tuning forks, you can pass this around or you can walk around. You can also maybe help them visualize this by putting it on something that's a little bit harder metal. This is a piece of aluminum I put together. And if you get it really close, you can see it wanting to bounce. You can also use just our quick quiz itself. If I put this on here and I take it to the edge of the paper, you can kind of hear that it's vibrating the paper and it's almost amplifying that sound. So those are a few things that we might want to do. But again, see if you can push your students to go back and think about how do they represent these vibrations. To help our students think through this, let's just think about what's happening with this piece of metal. When I strike it, it's going to cause it to deform, and the metal itself is going to want to try to come back to its original position. And what's happening is this is vibrating back and forth, each of these arms. Now, think about all of the air molecules surrounding this. According to kinetic molecular theory, we've got air molecules around us all the time. They're moving very quickly, bouncing off things. So imagine we have a randomized distribution of air molecules, and we can't see these very well, but we can pretend that we can make them as little dots. As I have those air molecules that are encountering this piece of metal, they randomly bounce off, and we end up with a generally random distribution. But as the arm is being vibrated, and let's take just one of the vibrations where it's swinging back out. Well, in this case, I had my random distribution of atoms or molecules, but now they're going to end up having this arm come over, and the number of hits that I had are now going to literally increase because I have this coming over. You can think of it as almost being a smaller volume. So I'm going to end up having these hits, and they're going to be tightly put together, a little bit denser, if you will, as compared to if the arm is swinging back like this. Each molecule that was going in that direction has to travel a little bit further to get it. In other words, what we're going to be doing is we're going to end up having less molecules. It's almost like we've increased the volume. We haven't really, but what we're doing is we're using a model that says each molecule is going to be hitting this a little bit less. So within a volume, we're going to have less molecules. And I know this can be difficult, so we can bring in something else here. And remember, these air molecules are going very fast. In the room here, we would say about 343 meters per second. Roughly about 700, 750 miles an hour. So very fast, hard to visualize. But we can use a spring to help us, our slinky, because these are called longitudinal waves, where we have the pressure wave, and that's really what's happening, and it's going in the same direction as the propagation of the wave itself. If I have a slinky, we can see the same thing. I can end up sending a pressure wave from one side to the other. And notice it goes right along the medium that I'm using. And in this case, you can see I end up having places where there's going to be a greater density of coils. They're very tightly wound as they move along. In other places, they're going to be rarefied or stretched out. And we can use this to help us follow the wave along. These are called longitudinal waves, and maybe we should start with our visualization process. So let's write this out. Longitudinal. Let's use air molecules at first. And maybe I'll draw this tuning fork at first. And I can say our tuning fork has an arm going out here and an arm going out here. Now let's just say randomly we would have air molecules that look something like that. They're just randomly distributed. But as this arm goes out, let's pretend that this arm is now swinging out. We have a velocity of air, and we said it was 343 meters per second. As the arm goes out, we're going to end up tending to get a higher density of those molecules. And then when the arm swings back, it's going to end up having fewer molecules. And then when it swings the other way, we can end up pressurizing the air in a little bit more of a concentrated fashion. Then it rarefies, and it kind of repeats this process. So we can see a pulse wave as it slowly moves along here. And then it's more dense, and then rarefied, more dense. So we can see this pulse wave is going to be moving along. Thankfully, the slinky allows us to see it moving a little bit slower. So that's one way to start visualizing our sound. But we have another way. But I need to set something up to help us with that. All right, I have a few pieces of equipment set up here. First thing we want to think about is how our ear picks up sound. If I have a longitudinal wave and I have pressure waves, they're coming along, they're going to go into my ear and down the canal, and I have a little membrane on my ear, which we'll call the eardrum, that's going to vibrate back and forth. And those pulses are really going to stop there. They're going to end up creating an electrical signal that goes to my brain, and then my brain will hopefully help me hear things. So we have that represented here. But this is a really difficult visualization. There's another type of wave called a transverse wave. Well, this is going to end up compressing and rarefying in the direction or along longitudinal wave. We have others where you can actually be at a 90-degree angle. In other words, the wave propagates one way and will displace 90 degrees from that. We're going to make a mechanical ear. And to do that, think of just like our eardrum. We need some way to pick up that sound. So we have to have some kind of area. Think of having this big paper cone. And as the waves hit that paper cone, it's going to cause that paper cone to move back and forth. Now, behind here, that paper cone is going to move a coil inside a magnet, and that's going to generate electricity. And that's going to allow us to use electricity on a visualizing device called an oscilloscope that hopefully we'll be able to hear and see at the same time. Let me make this much more sensitive. So now you can probably hear my voice. We are now taking these pressure waves and we're making them into a transverse wave, which we can see as a sine wave on our oscilloscope. So just like you might have seen this before, if I were to take a cup with my tuning fork, my tuning fork might not give off an awful lot of sound, but if I give it a greater area where it's vibrating the air, we might be able to hear a little bit better. We're going to end up using this resonance box that's going to amplify this a little bit so that hopefully we can see this. Pretty awesome. So now we can visualize my voice along with a pure tone. Mine has many tones, a gravelly, grumbly tone, where the tuning fork, this one is exactly 256 hertz. Let me put this off so I don't keep distracting you. I'll turn this way down. And let's draw out what a transverse wave is. Let's think of where we have rarefication. Rarefication would be here, and now we have a greater density of our coils. Well, if I were to take these, let's see if I can put them up here. Maybe I can make a little bit of a graph to show us how we can make one from the other. So I can take this right along here, and I'll start here. So every time that I have a stronger density of the air molecules, I can say they're going to have a greater amplitude. So right here, they'd have a greater amplitude. Here, they would end up being rarefied, almost zero. And then down here, back up here, rarefication, and it's going to be denser again, and then rarefication, denser right here, and then rarefied, and then denser. So we can end up seeing that we're going to end up having some kind of sinusoidal wave here, right? And so that's a transverse. And that's a transverse wave. So that's a really nice way of visualizing these. But both of these are going to have applications in a couple other features that we might not have thought about. Boom, 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 boom. What you can see here is I've made an earthquake detector. This is a seismograph. Look, we can't really visualize these pressure waves as well as we can with these transverse waves. And just so you know, sound is going by these pressure or longitudinal waves. We've just played a trick, which is nearly identical to how our brain works, where we can make these longitudinal waves through an electrical signal into a transverse wave. And then we can see them, and then we can use all of our standard mathematics for oscillatory motion. But notice how sensitive this is to the vibrations, especially the low frequencies, a big woofer like this. This has real applications. In earthquakes, we're going to end up having, well, first of all, let's think about what the Earth is. The Earth is, we can say, made of mainly solid, but it's kind of liquidy. In other words, once you get to the mantle, it's still solid, but it's starting to get a little bit pliable. But when you get down to the core, we can say, oh, that's kind of like more liquidy. Transverse waves don't really go through liquids. Longitudinal, no problem. So if I took the Earth here, and let's say that I had maybe the core, and this is the outside here. It's not to scale or anything like that, but I think we get the general idea. If I have an earthquake on one side of the Earth, we'll say right here, we end up having an earthquake event, and we are going to get pressure waves, P waves, or shear waves, they call them S waves. Well, they can go in all directions. But remember, we're going to end up having like a shadowing here. We're going to have a region, let's just say that's a liquid barrier here. And it's going to get more complicated than this. But we could say down here, we're going to end up having a shadow region where we're not going to see those transverse pulses coming through, but we will hear and hear. And by doing this and comparing that with the pressure waves, we can end up pinpointing where earthquakes are. So our model here has just made a really good seismograph. All right, that's your quiz for today.